290,000 degrees. Let that number sink in for a moment. That's the temperature of a star that's literally tearing space apart right now. 1,000 kilometers per second. That's the speed of the wind bursting from its core. 500 times faster than a bullet. This is the Red Spider Nebula, and it's absolutely real. 4,000 light-years away from us, in the constellation Sagittarius. A cosmic monster that's created a structure around itself thousands of times larger than our solar system. When Hubble first transmitted these images in 2001, astronomers were stunned. What they saw shouldn't have existed. 8 gigantic tentacles extending from the central star. Each one weighing 10 Earths. They're growing right before our eyes. And here's the most insane part, this structure is only 3,000 years old. It was born when the pyramids were being built in Egypt, and it's already dying. At the center sits a white dwarf, the hottest star we know. Our Sun. 5,500 degrees on its surface. This one. 290,000. Imagine a furnace 50 times hotter than the Sun, ejecting matter at speeds that would tear Earth to atoms in seconds. In 2007, scientists measured this velocity, 1,000 kilometers every single second. That's 0.3% of the speed of light. When such a hurricane slams into surrounding gas, boom. A shock wave reaching millions of degrees starts radiating X-rays. These 8 spider legs are exactly those explosions. Each leg moves outward at 300 kilometers per second. In 1 year, it travels 9 billion kilometers, from the Sun to Pluto and back. But here's the mystery, why exactly 8? Why not a circle like other nebulae? Scientists think there might be a second star there, invisible. It's orbiting nearby, warping gas flows, creating this eerie symmetry. But nobody's seen it. Maybe it's there, maybe not, the mystery remains unsolved. Now hold on tight. When astronomers pointed spectrometers at this nebula, they found an entire periodic table: nitrogen, hydrogen, oxygen, carbon, neon, iron, nickel. Where did all this come from? It was cooking inside the star for millions of years at monstrous temperatures. Hydrogen turning into helium, helium into carbon, carbon into oxygen. True cosmic alchemy. And when the star exploded, all of this burst outward. You know what that means? The atoms in your bones, the iron in your blood, the carbon in your DNA, all from dead stars just like this. We're literally made of stardust. Not a metaphor, but scientific fact. And this nebula shows us this process happening right now. In 2009, scientists compared 2 Hubble images, one from '99, another from 2007. 8 years between them, and the spider's legs had visibly grown. Some parts are moving at 450 kilometers per second. In 1 year they travel 14 billion kilometers, that's 93 times the Earth-Sun distance in just 1 year. The nebula is changing literally before our eyes. And in 2016 they found something else, a powerful magnetic field, thousands of times stronger than normal interstellar fields. Where did it come from? Maybe it's the star's own field. When it collapsed, the field compressed and intensified. Or maybe the turbulence in the gas itself generates this field through a dynamo effect. Nobody knows for sure. And here's another puzzle. The Chandra telescope looked at the nebula in X-rays and was shocked. It's shining much brighter than it should. X-rays are coming from somewhere in the filaments between the legs. What's happening there? Magnetic reconnection, like solar flares but thousands of times more powerful. Still a mystery. Now imagine you flew there in a spaceship. At 1 light-year distance, it's just a bright red dot. You fly closer, 1/10 of a light-year, and the star starts blazing like 1,000 suns. Around it, red glow, filaments, streams, gas vortices. Closer still, and you're inside the nebula. Red aurora in all directions, like northern lights but billions of times larger. Gas temperature is tens of thousands of degrees, but density is so low you wouldn't feel any heat. Giant gas waves rush past at hundreds of kilometers per second, but because of the low density, there's no wind. It's like standing in fog that's moving at hurricane speed, but you don't feel it, absolute madness. But there's a problem: radiation from the central star, harsh ultraviolet and X-rays tear molecules into atoms. Without powerful shielding, your ship would turn into a cloud of hot plasma in minutes. What will happen to the nebula next? In 1,000 years, the legs will be 3 times longer. In 10,000 years, the nebula will dim and start dissolving. In 100,000 years, it'll disappear completely. But the matter won't vanish. It'll become part of new stars, planets, maybe even new life. And the central star will cool, becoming a black dwarf in 1 billion years, a cold cosmic remnant drifting through the void. Why does all this matter? Because planetary nebulae are chemical element factories. Without them, there would be no terrestrial planets, no water, no us. In 2019, scientists used data from this nebula to refine stellar evolution models. Now we better understand what will happen to our Sun in 5 billion years. Let me tell you more about what makes this nebula so absolutely unique in the cosmos. You see, when we look at planetary nebulae, we're seeing the final gasps of dying stars. But the Red Spider isn't just any dying star. It's extreme in almost every measurable way. The central white dwarf is losing mass at a rate that's 1 million times higher than our Sun's solar wind. Every single year, it's throwing off matter equivalent to what our Sun loses over 1 million years. That's not gradual stellar evolution, that's cosmic violence. And the structure itself tells a story. Those 8 legs aren't random. They're the result of something we call hydrodynamic instabilities. When fast-moving gas slams into slower material, it doesn't just push through smoothly. It creates waves, vortices, eddies, like pouring cream into coffee, but on a scale that dwarfs our entire solar system. In 2018, researchers using the Keck Observatory in Hawaii employed adaptive optics to get crystal-clear images. They could see tiny details inside those legs, dozens of small knots, dense clumps of gas forming, growing, and disintegrating over just a few years. This is fluid dynamics in action on a cosmic scale. When fast flow pushes slow flow, waves form at the boundary. Just like wind creates waves on water. Except the scale is completely different, these waves are larger than the distance from Earth to Neptune. And then there's the chemistry. When spectroscopists analyzed the light from different parts of the nebula, they found something fascinating: the chemical composition isn't uniform. Different regions show different abundances of elements. The inner regions, close to the star, are dominated by nitrogen and oxygen. These are products of CNO cycle fusion, the process that powered the star when it was on the main sequence, fusing hydrogen into helium. But further out, in the older, slower moving material, there's more carbon. This came from a later phase of the star's life, when it was fusing helium into carbon in its core. It's like reading layers in an archaeological dig, except we're reading the star's life history written in atoms. In 2015, a team from the Instituto de Astrofísica de Canarias found traces of even heavier elements, sulfur, argon, even iron and nickel. These elements are incredibly rare in planetary nebulae. Their presence tells us something important about the star's mass and evolution. The star that created the Red Spider Nebula was probably 5 to 6 times more massive than our Sun. That's heavy enough to create these heavier elements through fusion, but not heavy enough to end in a supernova explosion. It's in this sweet spot where stars create planetary nebulae instead. Now, let's talk about that mysterious magnetic field. When astronomers conducted polarimetric observations in 2016, they measured how light from the nebula was polarized. Polarization tells us about magnetic fields. Charged particles spiral around field lines, and this affects how they emit light. The measurements showed field strengths of several milligauss. That doesn't sound like much, but it's thousands of times stronger than the typical interstellar magnetic field of just a few microgauss. Something is generating and maintaining a powerful magnetic field in this nebula. There are two main theories. The first is stellar dynamo. The white dwarf itself might have a strong magnetic field. As the star collapsed from a red giant to a white dwarf, its magnetic field would have been compressed along with it. This is conservation of magnetic flux, the same principle that makes a spinning ice skater speed up when they pull their arms in. The second theory is more exotic, turbulent dynamo. The chaotic motion of the ionized gas itself might be generating magnetic fields. Plasma is electrically conductive. When it moves in complex, turbulent patterns, it can create and amplify magnetic fields through electromagnetic induction. It's the same principle that powers Earth's magnetic field, but on a much larger scale. Which theory is correct? We don't know yet. Maybe both processes are happening. Maybe there's something else we haven't thought of. This is the frontier of astrophysics. And then there's the X-ray mystery. The Chandra X-ray Observatory has observed this nebula multiple times. X-rays come from extremely hot gas, millions of degrees hot. We expect to see X-rays from two places. First, right around the central star, where the stellar wind is accelerating to extreme velocities. Particles collide at such high speeds that they heat up to millions of degrees. That's straightforward. Second, at the heads of the spider legs, where fast wind slams into dense knots of gas. These are shock fronts. The fast-moving material crashes into the slower material like a cosmic car crash, heating everything to 5 million degrees or more. But Chandra found a third source. X-rays are coming from thin filaments between the legs. This wasn't expected. What could be heating gas to millions of degrees in these regions? One possibility is magnetic reconnection. This is the same process that powers solar flares. Magnetic field lines get twisted and tangled by the turbulent gas motion. Eventually, they snap and reconnect in a different configuration. When this happens, magnetic energy is suddenly converted to heat and kinetic energy. Boom, millions of degrees in an instant. But here's the thing, if magnetic reconnection is happening, it must be incredibly powerful and frequent to produce the X-ray brightness we observe. The magnetic fields must be constantly twisting, breaking, and reconnecting. The nebula is a seething cauldron of magnetic activity. Let me take you on a more detailed journey through what we'd actually see if we could travel to this nebula. At a distance of 1 light-year, about 6 trillion miles, the nebula would appear as a red star to the naked eye. You'd need a telescope to resolve any structure. At 0.1 light-years, 600 billion miles, you'd start to see details with a good telescope. The central star would be impossibly bright, radiating across the spectrum from infrared to X-rays. Most of its light is in the ultraviolet, which we can't see, but even the visible light would be blinding. Around the star, you'd see the red glow starting to resolve into structure. Not a smooth shell, but clumpy and filamentary. Streamers of glowing gas extending outward. You'd see motion, the gas isn't static. It's flowing, swirling, turbulent. At 0.01 light-years, about 600 astronomical units, roughly 15 times Neptune's orbit, you'd be at the edge of the nebula. Here's where it gets really spectacular. The red glow surrounds you in all directions. But it's not uniform. It's like curtains of light, sheets and filaments of glowing gas. The structure is incredibly complex, billows and waves frozen in time, except they're not frozen. They're moving. Slowly by human standards, a few kilometers per second, but that's faster than any rocket we've ever built. The gas density here is incredibly low, only a few thousand atoms per cubic centimeter. For comparison, the air you're breathing has about 10 to the 19th power molecules per cubic centimeter. That's 1,000,000 trillion times denser. So even though the gas temperature is tens of thousands of degrees, you wouldn't feel any heat. There's simply not enough matter to transfer thermal energy. You'd see the spider legs as massive structures extending away from the central region. Each leg is shaped like a teardrop or a finger pointing away from the star. At the head of each leg is a bright knot. This is where the fast wind is currently ramming into dense gas, creating a shock front. Behind each knot, the leg stretches out, getting dimmer as it goes. This is older material that was shocked earlier and is now coasting outward, cooling and dimming as it goes. And you'd see constant, subtle changes. Over days and weeks, you'd notice the knots moving outward. You'd see small eddies and filaments forming and dissolving. The nebula is alive with motion. But the real danger would be invisible. The central star is pumping out intense ultraviolet radiation. This radiation is ionizing all the gas around you, stripping electrons from atoms. An atom of nitrogen, normally with 7 electrons, might have only 4 or 5 left. Oxygen atoms are missing 2 or 3 electrons. This ionization is what makes the gas glow. When an electron recombines with an ion, it releases energy as light. The specific wavelength depends on which atom and which energy level the electron falls into. Nitrogen ions produce the characteristic red glow at 658 nanometers. But this same radiation would be deadly to unprotected matter. It would break apart any complex molecules. DNA would be shredded. Proteins denatured. Even metals and ceramics would be damaged over time. You'd need serious radiation shielding. And then there are the X-rays from the shock fronts and the central star. X-rays are even more penetrating than UV. They'd require thick lead or other heavy metal shielding. So while the nebula would be stunningly beautiful, it would also be incredibly hostile to any form of life or technology we can currently imagine. Now let's talk about the future evolution of this nebula. Computer models have simulated what will happen over the next thousands and millions of years. These models solve the equations of fluid dynamics, taking into account gravity, pressure, temperature, magnetic fields, and radiation. Over the next 1,000 years, the legs will continue to extend outward. The nebula will grow from its current size of about 0.5 light-years across to nearly 2 light-years. The central star will begin to cool. Its temperature will drop from 290,000 Kelvin to maybe 200,000. As the star cools, its ultraviolet output will decrease. This means less ionization of the surrounding gas. The nebula will start to dim. The bright red glow will fade. Over 10,000 years, this fading becomes dramatic. The nebula transitions from a bright, easily visible object to a faint, ghostly shell. The density of the gas continues to drop as it expands. Eventually, it becomes so diffuse that it's indistinguishable from the surrounding interstellar medium. By 100,000 years from now, the Red Spider Nebula will have essentially disappeared. The gas will have mixed with the interstellar medium. The atoms that once made up the star's outer layers are now spread across light-years of space. But those atoms don't disappear. They become part of the great galactic recycling program. The interstellar medium isn't empty, it's full of gas and dust. This material eventually gathers into giant molecular clouds. These clouds are the birthplaces of new stars. So the nitrogen, oxygen, carbon, and other elements from the red spider will eventually become part of new stellar systems. Some will end up in planets. Some might even end up in living organisms, billions of years in the future. Meanwhile, the central white dwarf continues its lonely journey. With no fusion to support it, it has no internal energy source. It simply radiates away its stored thermal energy. This is a slow process. It takes billions of years for a white dwarf to cool from hundreds of thousands of degrees to near absolute zero. In a billion years, the former red spider star will be what we call a black dwarf, a cold, dark ember drifting through space. It will be invisible except through its gravitational influence. It's a stellar corpse, the final endpoint of stellar evolution for stars like the one that created this nebula. But even black dwarfs aren't truly the end. Over timescales so vast they're hard to comprehend, 10 to the 32 years or more, even the atomic nuclei in a black dwarf might decay through quantum tunneling. But this is so far in the future that the universe will be almost unimaginably different from today. Why do astronomers spend so much time studying planetary nebulae like the Red Spider? There are several crucial reasons, each touching on fundamental questions about the universe. First, they're laboratories for extreme physics. The conditions in these nebulae, the temperatures, densities, radiation fields, magnetic fields, can't be reproduced on Earth. We can write down the equations describing the physics, but we can't test them in the lab. Planetary nebulae let us test our understanding of physics in regimes we can't access any other way. For example, the shock waves in the Red Spider are supersonic, faster than the speed of sound in the gas. These are called bow shocks, and they're crucial for understanding how energy propagates through astrophysical plasmas. We see similar shocks in supernova remnants, in the solar wind, in galaxy clusters. Understanding the Red Spider's shocks helps us understand these other phenomena. Second, planetary nebulae are chemical enrichment factories. Stars are where heavy elements are created. Hydrogen and helium came from the Big Bang, but everything else, carbon, nitrogen, oxygen, all the way up to iron, is made in stars. During their lives, stars fuse lighter elements into heavier ones. But these elements are locked inside the star. It's only when the star dies and ejects its outer layers that these elements are released into space. The red spider has returned to space all the carbon, nitrogen, and oxygen it created over its lifetime. This enriched material will eventually become part of new stars. Those stars will have higher metallicity, a higher abundance of elements heavier than helium. Planets form from this enriched material. Earth is made of elements that came from dead stars. The calcium in your bones, the iron in your blood, the carbon in your cells, all forged in stellar furnaces billions of years ago. Without planetary nebulae and supernovae returning this material to space, there would be no rocky planets. No water. No complex chemistry. No life. Third, studying planetary nebulae helps us understand stellar evolution. Stars are born, live, and die. We have mathematical models describing this process, but we need observations to test and refine those models. The red spider tells us about stars in a specific mass range, roughly 5 to 6 solar masses. These stars are massive enough to create planetary nebulae but not massive enough to explode as supernovae. They represent a crucial transition point in stellar evolution. By studying how these stars die, we learn about their lives. What nuclear reactions occurred in their cores? How did they lose mass through stellar winds? How did their internal structure change over time? In 2019, researchers from the University of Arizona used Red Spider data to calibrate models of stellar mass loss. They improved our understanding of how efficiently stars shed their outer layers in the final stages of evolution. These improved models are now used to predict the fates of thousands of other stars. And this has practical implications. We want to know what will happen to our Sun. In about 5 billion years, it will run out of hydrogen fuel in its core. It will swell into a red giant, probably engulfing Mercury and Venus, possibly even Earth. Then it will shed its outer layers, creating its own planetary nebula. Will that nebula look like the red spider? Probably not. Our Sun is less massive, so it will evolve differently. But studying nebulae from a range of stellar masses helps us bracket the possibilities. Let me tell you about the incredible technology and teamwork that goes into studying objects like the red spider. It's not just one telescope or one team of scientists. It's a global effort spanning decades. Hubble Space Telescope has observed this nebula multiple times, in 1999, 2007, 2015. Each observation used different cameras and filters. The filters are key. There's a filter that only lets through light at 656 nanometers. This is the hydrogen alpha line, emitted by hydrogen atoms. Another filter at 501 nanometers captures doubly ionized oxygen. One at 658 nanometers gets ionized nitrogen. By combining images through different filters, astronomers create false color images where different elements appear in different colors. Red might represent nitrogen, green oxygen, blue hydrogen. This isn't what you'd see with your eyes, but it reveals the chemical structure of the nebula. Ground-based telescopes contribute too. The Keck Observatory in Hawaii uses adaptive optics, a technology that compensates for atmospheric turbulence. The atmosphere makes stars twinkle, which is pretty, but it blurs telescope images. Adaptive optics measures these distortions hundreds of times per second and adjusts a deformable mirror to cancel them out. The result is images nearly as sharp as if the telescope were in space. The Very Large Telescope in Chile has conducted detailed spectroscopy of the nebula. Spectroscopy spreads light out into its component wavelengths. By analyzing the spectrum, astronomers can determine the temperature, density, composition, and velocity of the gas. Radio telescopes observe the nebula at millimeter and centimeter wavelengths. They detect cold gas and dust that don't glow in visible light. This reveals different structure than optical images. The Spitzer Space Telescope observed in infrared. It found dust grains heated to a few hundred degrees Kelvin. These grains are made of carbon or silicates, minerals. They formed in the cooling ejecta from the star. Chandra X-ray Observatory sees the hottest gas, the million-degree plasma, in shock fronts. It revealed structure invisible in any other wavelength. All these observations together paint a complete picture from radio waves to X-rays. From cold dust to million-degree plasma. From dense knots to diffuse outer shells. It's like solving a jigsaw puzzle with pieces from different sources. And the data doesn't just sit there. Theorists build computer models trying to reproduce what we observe. These models solve complex equations, the Navier-Stokes equations for fluid flow, Maxwell's equations for electromagnetic fields, radiative transfer equations for how light propagates through gas. The models make predictions. Then observers check if those predictions match reality. When they don't match, theorists refine their models. This back and forth between theory and observation is how science advances. For the red spider, one major question is still debated: is there a companion star? Some models suggest the bipolar structure requires a binary system. The gravity of a second star would create a dense equatorial disk while allowing fast winds to escape along the poles. This could explain the eight-legged structure. But searches for a companion have come up empty. If it's there, it must be faint, maybe a low-mass star or a brown dwarf. Or maybe the structure was created by rapid rotation or a strong magnetic field instead. We don't know yet. Despite decades of research, mysteries remain. How exactly do those legs form? We know its hydrodynamic instabilities, but the details are unclear. Why is the central star so hot? Standard models predict maximum temperatures around 200,000 Kelvin, but this star exceeds that. What's happening that we don't understand? Where does the excess X-ray emission come from? Shocks explain part of it, but not all. Is it magnetic reconnection? Something else? These aren't failures of science. They're opportunities. Every unanswered question is a chance to learn something new, to refine our theories, to develop new observational techniques. And that's the beauty of science. It's never finished. There's always more to discover, always deeper to look, always another question to answer. The Red Spider Nebula teaches us profound lessons. First, it teaches humility. Here's an object 4,000 light-years away, so distant that its light has been traveling toward us since before recorded history began. Yet it's tiny on cosmic scales. Our galaxy contains billions of stars, and the observable universe contains hundreds of billions of galaxies. This nebula is one death of one star in one galaxy. And yet it showcases forces that would obliterate our entire planet in seconds. Temperatures that melt any material. Magnetic fields stronger than anything we can create. Energies beyond our comprehension. We are small. Our planet is small. Our existence is fragile and temporary. The universe doesn't care about us. It operated for 13.8 billion years before we existed, and it will continue long after we're gone. But here's the paradox: even though we're small and temporary, we can understand these cosmic processes. We can look at a nebula 4,000 light-years away and figure out its temperature, composition, velocity, magnetic field strength. We can reconstruct its history and predict its future. Consciousness, awareness, intelligence, the ability to ask questions and seek answers, is precious precisely because it's rare and fragile. As far as we know, Earth is the only place in the universe where matter has organized itself into structures capable of understanding the universe. The red spider also teaches us connection. We are not separate from the cosmos. We are part of it. Every atom in your body except hydrogen was created in a star. The calcium in your bones, the iron in your hemoglobin, the carbon in your DNA, all forged in stellar nuclear furnaces. You are literally made of stardust. This isn't poetry. It's physics. It's chemistry. It's truth. When you look at the Red Spider Nebula, you're looking at a star returning material to the cosmos. Billions of years from now, those atoms might be incorporated into a new planetary system. Some might end up in a planet. Some might become part of living organisms. There could be future beings, made from the atoms the red spider is dispersing right now, looking up at their night sky and wondering about their place in the universe, just as we do. This is the great cosmic cycle. Stars are born from clouds of gas and dust. They live for millions or billions of years, fusing light elements into heavier ones. They die, returning enriched material to space. New stars form from this material. The cycle continues. Our sun will die too. In 5 billion years, it will swell into a red giant. It will lose its outer layers. It will create its own planetary nebula. Some future civilization, if any survive that long, might observe it and wonder about the star that once warmed Earth, the planet where intelligence first arose in this solar system. Everything is temporary. Stars, planets, galaxies, even the universe itself has a finite lifetime. But while we exist, we can observe, wonder, learn, and understand. That's what makes us human. The Red Spider Nebula is more than just a pretty picture. It's a testament to the universe's complexity and beauty. It's a reminder of our cosmic heritage. It's a window into processes that shape the evolution of galaxies. It's a laboratory for physics we can't reproduce on Earth. And it's a source of endless questions. Questions that inspire the next generation of astronomers. Questions that drive technological innovation as we build better telescopes and develop more sophisticated models. Questions that might not have answers yet, but that's okay. The journey of discovery is just as important as the destination. As we continue to study the red spider and thousands of other celestial objects, we're writing humanity's story in the stars. We're figuring out where we came from, understanding where we are, and glimpsing where we might go. This nebula, this beautiful, violent, ephemeral structure in the constellation Sagittarius, connects us to the deepest questions of existence. How did we get here? What are we made of? What is our destiny? The answers, written in light and gas and magnetic fields across the cosmos, are waiting for us to decode them. And that's the magic of astronomy, the wonder of science, the beauty of human curiosity reaching out to touch the infinite. The Red Spider Nebula. A cosmic predator. An element factory. A physics laboratory. A reminder of our mortality and our potential. One of the most spectacular sights the universe has to offer. And we've only just begun to understand it.